Okay, so does everybody have a chance to copy the notebook? When yes. Okay, so today we're going to make our first neural network. And we're going to use it with Keras, which is an API or library that comes with the TensorFlow from Google. And it just makes it really nice and easy to build a neural network. So we'll start from the basics. I've put some links here for some of the libraries that we're using. So there's TensorFlow, Keras. These are the deep learning libraries. And then NumPy and Pandas are used for our data manipulation. And Seaborn and Matplotlib are used for data visualization, so graphing. And scikit-learn is a general machine learning library. So you're welcome to look through those. The websites will have lots of documentation on what are the different functions that come with them, how to access them, what you can do with them. So to start, we need to import a bunch of libraries, and I've listed them all here. And common question is, if you're new to coding and you look at this and you think, like, how do I know to import all these things? Well, for some of them, it's simple. Like, you're working with data, so you're going to need the Pandas and NumPy, which are the data libraries. You're making a neural network, then you're going to need Keras and TensorFlow. If you're not going to be graphing, you can use Seaborn or Matplotlib, and choose one or the other. And sometimes you don't know what you're going to import until you get to a point where you want to do something and you don't know how to do it. So you go to Google and say, hey, Google, how do I do this? And then Google will tell you, oh, you need to import this, so you can use this function from this library. And then you go back up to your libraries and type it in. You'll find there's a lot of that in coding if you're fairly new to it. So I can explain these as we use them. I'll just run this first. This one is a special thing we'll come to later. This lets us do some visualization. Okay. First thing we need to do if we're making a neural network is we need data. And what data are we going to use? So this one is a fairly widely used data set, especially for intro machine learning or intro to neural networks. So I'd recommend everybody go click on the link, download the data if you want to follow along. And this is a data set of various different risk factors for developing diabetes in the Pima people. And it's the website goes to a website called Kaggle, and this is a common website for machine learning competitions. A lot of data is posted there. And let's see if I can. Okay, can you see the website here? So it'll give you descriptions of what the data is. And so some of the risk factors here are whether they've been pregnant or not, what the blood glucose is, the blood pressure is, and all of those are listed in columns, and whether or not a particular patient went on to develop diabetes. Okay, so first thing we need to do is load the data, and you can simply, once you download it, you can drag and drop into our file folder here, or you can click on the upload icon and do it this way. So step one is do that. Next, we need to convert it into a pandas data frame. So it's already stored as a CSV file. CSV stands for comma separated values. Basically just a text file that uses commas to separate columns and rows. So here we're going to call this data frame DB data, or diabetes data. You can call it whatever you like, whatever makes sense to you. And then there's a function in the pandas library, which, go up to the imports, we've imported pandas as PD. You can import it as whatever convenient shortcut you like. PD is fairly standard. So within the PD pandas library, there's a read CSV function. And if you're using a Google Colab, it has a neat feature where if you start typing the function, it'll come up with a whole bunch of documentation on the function that you're using. And it can look a little overwhelming at first, but if you follow along, then you'll find where it says def. If you remember from our first workshop, def defines a function, and then here's the name of the function, and then within the brackets, there's the first one here, and can you see my pointer? Just to make sure.
Yep.
Yeah, okay. And then the end bracket here. And within that are all these different arguments or parameters that you can use to customize how you want this function to work. And of course, it's a whole lot of nonsense at first, but it'll further down, scroll down, it'll explain sometimes clearly, sometimes not clearly, what each thing does. So, for example, header. Is there a header or not in the data file? And if you open up the CSV, this particular one, you'll find there is no header. So we'll say header equals none. And a lot of times you don't need all of these, but they're there as options, and you can read through them as you need to. So we're going to read the CSV, and we're telling it that it has no header. Okay. Now here, there's another function called head, which will display the first 5 rows of the data frame, or it's a method rather. So we hit that, and here we have our data, and it doesn't have named labels, so you don't know exactly what's what, but you can, if you look back at the Kaggle website, it'll tell you which column is which. And if we get rid of this header, you can see what happens. Then it takes the first row and sets it as a header, because it's assuming that there's a header there. That's the default assumption. So we specify that there is no header. And it's always good to take a look just in case something like that happens and you didn't, you don't want to lose some data for a little error like that. Okay, then another thing you can look at, it's always good to look at the data, see what's going on. So here we're printing out the shape of the data. That's this line here. So there are 768 rows and 9 columns. So that'll be 9 different categories or features, different risk factors for diabetes that we're looking at, and 768 patients. And then this one, the D types, short for data types. This lets you see what kind of data is in each column. So these are integers, integer, 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 and then float. If you remember, float is basically anything with a decimal point. So you can see in row 5 here, or column 5 and 6, those are floating point numbers or decimal numbers. And then our last column here is our target column. This is whether they have diabetes or not diabetes. 1 is diabetes, 0, no diabetes. And you can also use the describe method to show some basic statistics. And very important is this first row. The count should be the same in all of the columns. If they're not the same, then one of your rows is missing some data. And I'll look at the mean, standard deviation, minimum values, maximum values, and the quartiles. So hopefully you're familiar with statistics. If not, that's okay. So now we've looked at the data. Maybe you want to look at it in a better way with pictures, because we are humans and we like to look at things. And again, this is Seaborn, which is a pretty nice way to display the graphs. And this one is abbreviated commonly as SNS. Apparently, if you watch The West Wing, there's a character, last name of Seaborn, and these are his initials. So there's a lot of little inside jokes like that in computer science, if you know where to look for them. And for example, if you're learning Python, you might want to check out Monty Python, very popular amongst computer scientists. That's also where we get the word spam from. I'll send a link to the spam sketch for those interested afterwards. So yeah, this is a little inside joke. You can always import it as whatever you like, but this is a common one. So we're going to use the pair plot from Seaborn. And again, if you start typing the function, it'll tell you information about it. And you can always go to the Seaborn website, look it up, and that'll give you probably a nicer view of what to do with it. So we're feeding it our data. We're coloring our 8th column, which is our target column, and giving it different variables, which will be our other columns. And we're just going to do column 0 through 4, because it takes a little while to generate the graphs. Should have some waiting music. Yeah, the specific function. So for example, I'll just, oops. So if I start typing the function, then information on that specific function will show up. Okay, and this is what our data looks like. Orange dots are the default. Orange is the default hue. There are ways to change that, but orange will be every data point that has diabetes. And you can see, is there, like here, there's a kind of a clear separation between them here. Over here as well. Let's take a look what kind of visual correlations you can make. Okay, and then we also look at our target. And so here we're calling just the 8th row, or the 8th column. And there's a function called value counts. So it'll count all the values in our 8th column, and we're going to print it out. So we'll do that first. So there's 500 zeros, which are no diabetes, and 268 ones, which are diabetes. And we can also graph it with a Seaborn count plot, where we set X to our target column, and then label it with the count. So here's no diabetes and diabetes. So it's about 1/3 of the data set are diabetic. And you can also use matplotlib. This will show a histogram, and this just chooses the size of the histogram. If you remove the size, that's too small. So you can make it as big as you like. This is 12 by 12. And this just shows it. And it lets you see a distribution of the data. This one's binary data. And it's good to look for anything that looks out of the ordinary, anything weird. But this looks okay. Okay, so now we have our data, loaded our data. We've looked at it, everything looks okay. And we kind of have an idea of what we're working with. Now we can start training and building the neural network. So first thing we need to do is to separate our data into features and the target. So we don't want our neural network to know who has diabetes or not just yet. So our features, these are the columns, these are all the risk factors, whether they're what their blood glucose is, and whether they're ever pregnant, things like that. We'll call that X. And we're going to do, this is our data, diabetes data. I use a drop method. And again, if you hover over it, it'll tell you drop is a function, and there's a bunch of different things you can do with it. So we're going to drop our 8th row, or 8th column. And axis just tells you that it's going to be columns. 1 will be columns, 0 will be rows. So we're dropping 8th column. And then we're going to use our head, as we did before, which just shows the first 5 rows. And we can see our 8th column is gone, just as we wanted. Now for the target for Y, we want just the 8th column. So we can say just 8th column of our diabetes data. And run that, and there we go. This column here is just our index or identifiers, but this is the data. Is that making sense so far?
Yes.
Okay. So now we've divided it up into our X and our Y, training set and our targets. Now we need to split it into train and test sets. So there's a function here called train test split, and I believe this belongs to Keras. Or no, this is sklearn. So from sklearn, we've imported train test split. And this makes it really easy to split up your data. So for train test split, we give it our features, then our target, and then the test size. So this will be the percentage of the data we want to remove and set aside for testing. So 0.2 will be 20%. And then random state, this is basically just a seed number for random number generator. And this is important for reproducibility. So if you set it to 42 here, the answer to a life universe and everything, if anybody's familiar with Hitchhiker's Guide from the Galaxy, lots of nerdy things in here. Yeah, but if you want somebody to reproduce this, then they need to use the same random seed so that it'll be consistent. Otherwise, it can be a little unpredictable. Okay, so this is our train test split function, and this will split it up into 4 different sets of data. There's going to be an X train, X test, a Y train, and Y test. So we have to name all 4 of those variables, and you can call them whatever you like. Here it's just X train separated by commas, X test, Y train, Y test. So this will generate 4 different data sets and assign them in order to each of these. And then just have some print functions to printing the shape. It'll tell us how many columns and rows in each one. So after it's done the split, in our X train, we've got 614 rows, 8 columns. And in this would be a Y train. We've got 614 rows and just a single column. And same with the test. It's always good to check to make sure that these numbers match up. Otherwise, you're going to have trouble later. Okay. Next thing we want to do is normalize the data, transform the data to a range between 0 and 1, because you can have all kinds of different numbers, and it just makes things so much simpler for the neural network to understand if everything is between 0 and 1. So there's another convenient function called min-max scalar. So what we're going to do is create a scalar. You can name it whatever you like. And this is just a variable name. And then we'll do a min-max scalar. And we fit the scalar to our training set. And the reason we do that is because that is the data that it's training on. And if you fit it on the test set, for example, then it's not going to see that until after it trains. So you want to fit it to the training data. And then you want to apply it, use the scalar, that's what we call it here, and transform our training set. And use the same scalar to transform our test set. And you can call these whatever you like. So I've called it X-train norm for normalized and X-test norm for normalized. And we don't need to normalize our Y, our target, because it's already 1 or 0. Okay, so we'll scale that. And if we want to take a look, we can always do our take a look. And you can see all the values are between 0 and 1. Okay, now we get to actually make a neural network. And this uses Keras. So first thing we need to do is, usually we call it a model. You'll hear that word a lot in machine learning model. You don't have to call it a model, but that's the convention. So we'll make a model and make that equal to a sequential model. Sequential model just means that it'll go through each layer sequentially. And we're bringing that in from Keras, so keras.sequential. I might just, as an aside, add a note about imports. I'm not sure we covered that in the intro to Python. But there are different ways of importing. So you could import, you could say from Keras import sequential. If I did that, then I wouldn't need to add the Keras dot. But what I've done above is I've just imported Keras. So you have to, so that means we don't have sequential within our environment as sequential. It's still within, we've imported all of Keras and it's within Keras. So we need to say Keras.sequential in this case. That's just an aside. You'll see both things. Okay, so we've made our model and now we need to add some things to it. So first we need to add the input shape. So our input is going to be 8 columns. So we're going to model.add keras.input, and we'll give it a shape of 8 comma. And so it's important to do 8 comma because it's expecting like rows and columns, and you need to give it like it usually takes in a matrix array. So in this case, we just have an 8 by 1, and you don't need to say 1. It's 1 by default. But if you have anything bigger, especially with images, which are like 1024 by 1024 pixels, then that's what your shape will be. But here it's not much simpler, so we got 8 comma and nothing else. So now we've defined our input shape. Now we can start adding some nodes, some neurons. Next we use model.add. This time we're adding dense layers. So again, this is within layers within Keras, and then dense is within layers, which is within Keras. It's just like a file structure. Again, you could always import directly dense, and then you wouldn't need these. So dense refers to a fully connected layer. So if you have, that means that all the neurons will connect up to each other. And that makes those dense images that you may have seen before. We'll have the circles connected to each other. So we're using a dense layer, and we're putting in 12 neurons. And we're using ReLU activation. If you watched our first A-stream lecture, we would have talked about that a little bit. But this is a rectified linear unit. And what this does is it'll take any input, and if anything is less than 0, or negative, it'll set it to 0. Anything that's positive, it'll pass on. So we made one layer with 12 neurons, and then we can add another one, this time with 8. And then our last layer here, we only want 1 neuron. because it's going to tell us either yes or no. And we're using the sigmoid activation. Sigmoid will take whatever input it gets and outputs either a 0 or a 1. So because we have, we're looking for either is diabetes or is not diabetes, it's binary classification, 0 or 1, so we use sigmoid. And this I'll come back to in a little bit, but let's just run that. So now we've made our model. Now we need to compile it with the model.compile. And there's a few things you can use to help with the performance. The first one we're going to do is an optimizer. This is a common one called Atom. This basically optimizes the learning rate. I won't go into the details of how, at least not today. And then the loss. Again, if you've listened to our first lecture, the loss can I discuss how to decide the number of layers and nodes within a layer. So generally, the bigger your data, the bigger the layers, and the more nodes you'll need. So we have about 614 by 8 data points. And for each row, we've got an input of 8. So if we have about 8 inputs, I mean, a lot of this is arbitrary, but it should be not too what's the best way to say this? It should be kind of scaled to the amount of data you have. It's just to find a starting point, and then you give it a try. A lot of trial and error. Actually, I'm going to give you guys some homework on trial and error. There'll be a few things you can adjust and play around with to see if you can optimize this. But yeah, it should be kind of similar within reasonable scale of your data. It's fairly arbitrary. Okay, so back to the loss. This is our loss function. This is what will evaluate how accurate or how close the outputs are to what we want. And because it's a binary problem, there's a binary cross entropy loss function. There are other loss functions for different types of data, but in general, for binary classification, we use binary cross entropy. And then metrics, there's a variety of different metrics that can, or ways of evaluating how well this is performing. We're just going to look at accuracy, but there's lots of others you can choose. And those will be, you can find those in the Keras documentation if you want to add some more. And then this will compile it, and then we will print a summary of the model. So model.summary. And this lets us see what we have. So we have our 3 layers here. Our first one with 12 neurons, second one with 8, and this one, our last one with 1, and the number of parameters they have. Okay. Excuse me. Now this is this will create so does it mean that the layers are determined by inclusion or exclusion criteria? I'm not sure what you mean by that. Can you elaborate? Anyway, I'll continue. So this line this will make a folder over here called logs, and that'll store some information for later display. And then this creates a callback for TensorBoard. TensorBoard is just a nice display that TensorFlow provides, and I'm not going to explain it in detail, but we'll see later. Basically, we make a callback, and okay, sorry, there's a follow-up on the question. Do you have to put some conditions in the data? So you don't necessarily have to reduce the number of neurons in each layer. Sometimes you can increase them, then decrease them. And no, you don't. I don't. Still not quite sure what you mean, but oh, maybe so for inclusion. Why don't I get to that question afterwards? And I'll keep moving. Okay. So don't worry about this too much. This will show up in a second. So now we're going to fit our model to our data. So we need to give it our training data and our target for our features. So this will tell it whether it's right or not. Then you can choose a batch size. So how many data points is it going to use for each training epoch? In this case, we're using 10. And this is one of the arbitrary things you can play around with. And then you can choose a number of epochs, a number of times, number of rounds of training it'll do. Verbose, this will give a printout of what the model is doing, and then you give it the validation data. So we got our X test and Y test. For training, we have the train, and for validation, we got our test. And then this callback is the TensorBoard callback. That'll just let us see the data. Okay, let's run this. Yeah, so it's going through 150 training epochs. And if you look at the loss here, ideally the loss should be decreasing and the accuracy should be increasing. And you'll find that it doesn't always do that. And then you have to adjust things and try again and readjust and try again and readjust and try again. Okay, so what do we have? We have loss about 0.44. Could be better. Accuracy about 77. Also could be better. But that's a good start. Okay, and then this is the TensorBoard. I'll give it a minute to load here. And if we look at so to give us the graph of our training on the bottom and our validation at the top. So ideally what we want is for both of these to come down and converge. So val loss is, so this is the loss in accuracy from the training data, and this is the loss in accuracy on the validation data, the test data. So it'll train it, get these values, and then it'll give it the test data and see whether it gets similar values or not. Okay, so this is not ideal, but it's a start. And in order to improve it, you can try different things. One thing you could do, you could increase the number of epochs. You could try increasing the batch size. Let's say we go with twice as many data points in the batch. Then we could run it again, see what happens. We could try, or maybe we want another layer in here. We could try that. So we'll run that. And give another try, see what happens. And sometimes you'll make it worse, and hopefully make it better. Yeah, we got a little bit better than last time, but it was jumping around a bit. And if we go down to here, we can refresh TensorBoard. It's showing both at once. Not sure why. So anyway, so yeah, so one thing that can happen is you can overfit to the data, and if you find that your loss in accuracy, let's say you get 0.001 loss and 0.99 accuracy, but the val loss and the val accuracy are way off, then that would mean you're overfitting. And if that happens, you might want to add a dropout layer. So to go back up to the neural network, you can model.add a dropout layer. And what this will do is it'll randomly remove 30% of the neurons in the layer. And you can put that at the end of every layer, except your last one, because that's your important one. You don't want to lose anything there. So we can run it again with some dropout. And usually with dropout, the training will be a lot slower. So you may need to increase the number of epochs with dropout. And it's not quite as good as before. We probably need to adjust some things again. But we'll do that in a future workshop where we work on optimization strategies. So once you've trained your model and are satisfied, this is not a satisfying value, but we'll keep it at that for now. Then your sklearn has some metrics for evaluating. And so we're looking at the, I didn't use all of these. There we go. So this will evaluate our test sets, and it should be similar to what we got up here. And our loss on the test set is about 0.5, and our accuracy is about 77%. Not great, but it's a start. And then there's also some more data you can get from here. with a precision, a recall, F1 score. But we'll just focus on the loss and accuracy for now. And finally, once you're done and you like how your model works, you can save the model. And usually these are .h5 files. This is a file of all the weights that are applied to your neural network. So what it's doing when it's running here is it's changing the weights at every epoch, trying to find the optimum values. And then this will save all those values. And you can see it here. And you can always download that and save it for later and re-upload it. And if you want to load it, you can do it this way with you can call it whatever you like, new model, for example, and then from TensorFlow, Keras, models, there's the function load model. And if you're wondering how do I even know that load model is in all of these, well, you go to Google and say, how do I load a model in Keras? And it'll tell you. Or you can go to Keras documentation and search for loading models, and you'll find it there. Or you can ask somebody that knows how to do it, and they'll tell you, find it in Keras models. But in coding, Google is your friend. You'll do a lot of Googling. So we can run this, and this loads the model, and this is a summary just to show what the model looks like. All right, so that's the basics of making a neural network. It's fairly easy to actually make it with Keras. You just put in a couple of layers, tell it the number of neurons, and choose an activation function. Does this all make sense? Okay. And there is a whole lot of trial and error, whole lot of adjusting. And so some of the things you can play around with on this file, on this our notebook, COLAB notebook, are you can play around with adding more layers. You can add bigger layers. You can add more neurons. You can try different dropout values. You can try with or without dropout. You can comment out the dropouts. Other things you can do. So this atom comes with a default learning rate. You can adjust the learning rate. Is there code to help visualize the nodes and layers used in the neural network? I'm sure there is. I'm not aware of it. Yeah, I'll see if I can find a way to visualize the network. The problem with that is sometimes if you have a lot of data, the networks can be enormous. Okay, and yeah, and other things you can play around with. Oh, thanks, Sarah. Other things you can play around with are batch size. And again, choosing a starting batch size will depend on how big your data is, how many data points you have. So if you have, like we have about 600 data points, I think, then 20 is appropriate. But if you have 1,000,000 data points, maybe you'll want 5,000, 10,000 in a batch. And epochs, you can go up to 1,000 or more. But when you're playing around with epochs, you'll want to watch the loss. And if you have something that's converging, you'll find that the loss will go down to a certain point, and then it'll stop, and then it doesn't change anymore at that point. And if it's still going, then you have too many epochs. Or if it starts increasing again, Sometimes it'll decrease and then start diverging again. At that point, you have too many epochs. But if it never decreases enough, or it's decreasing but very slowly, then you might want to increase the learning rate or increase the number of epochs. So a whole lot of things to adjust. And there's also different optimizers besides Atom. I'll post a link on from Keras explains a few of these. I'll post a link on what some of those are and how you can adjust those as well. But we'll cover those details in I think either next workshop or 2 workshops from now. But yeah, feel free to play around with the code here. And I would recommend just for fun is to make your own. Just start a new notebook, new Google Colab notebook, and just type it out. Just copy it. It's a good way to get used to what everything does, and it helps program your mind about how to type code and how to use some of these things. So I'd recommend that if you have the time. So I hope this was helpful. And yeah, play around with it and have fun, and let us know if you have any questions. We're happy to answer them. Okay, thanks for coming. No more questions?
Can I just ask a question? So how often do you have to play around to get to the right point? Is it depends on the data and depends on your expertise, or there's a set pattern of doing it that will get you there quicker?
So there's a few things you can, well, yes to all of those. So most important thing is if you try a few things and really nothing changes, likely the problem is in the data somewhere. Either it hasn't been prepared properly or cleaned properly, or maybe maybe it's not labeled properly. So that's one of the first things to look at. And yeah, I don't know if there is really any method to it. Sarah, do you know if there's any method?
It's definitely looking at what other people are doing for similar problems and trying to kind of adapt what they have. I think, the information is kept somewhere in the collective consciousness of all the data scientists and ML engineers. But, it's definitely learning from others and testing things out yourself. And that'll help you, I guess, get an intuitive sense of what the architecture should look like.
And maybe something that might clarify that a bit, or put it in a different perspective, is that every time you train your model, it's often referred to as an experiment, because you don't really know what's going to happen. So I think that may have given you more questions than answers, but that's the state of the field. All right. Any other questions? Okay, we'll end it there.